So in order to have a good discussion about gases, one of the things that you have to understand are a couple of mathematical relationships. Those mathematical relationships are direct relationships. And a direct relationship is when one variable increases, another variable increases as well. Those two variables are then directly related to one another. So what that means is the opposite can also be true. As one variable's value decreases, another variable's value decreases. So those two variables would be directly related to one another. So an indirect relationship, on the other hand, is one in which one variable increases, another variable decreases, or one variable decreases, the other variable increases. So that's just some important things, important definitions to kind of establish, because we will be talking about pressure, volume, gases, and temperature and everything like that. So whenever we talk about these different gases and the relationships between gases and other property, or sorry, individual properties of gases, we can talk about a couple of different laws. The first law is Boyles Law. Boyles Law shows the relationship between pressure and volume. So pressure times volume gives you a constant. Now, at constant amount and constant temperatures, that's what you're going to end up with. So if you do not vary the amount or the temperature of a substance, then there is an indirect relationship between pressure and volume. So as one gets smaller, the other one's going to get bigger. So as the pressure, for instance, is going to increase, well, that means the volume is going to decrease, so long as you have not changed the amount or the temperature. So I always try to think about this in terms of, like, let's say that I had a 2-liter bottle of Dr. Pepper, and there's my 2-liter bottle of Dr. Pepper, and all I've gotten there is just gas. Now, let's say I were able to take that exact same amount and put it into a 20-ounce bottle of Dr. Pepper, and there's my 20-ounce bottle of Dr. Pepper. The exact same amount of gas that filled this, I've taken it and I've transferred it to this bottle. Okay, so now what's going to happen? My volume has gone down. So if I press the sides of this, if I'm holding that bottle, in this case both of these are closed, if I press the side of that 20-ounce bottle, well, it's going to feel more kind of taut, because of the fact that I have decreased my pressure, decreased my volume, my pressure goes up. There's an indirect relationship between pressure and volume. So Boyle's law kind of describes that indirect relationship between pressure and volume. Now, if you go on from there and talk about Charles's law, Charles's law is a relationship between volume and temperature. And what ultimately it means is there is a direct, or what it kind of explains is there is a direct relationship between volume and pressure. So if the volume volume and temperature, as the volume goes up, the temperature also is going to go up. Charles's law also gives us a little bit of an explanation or insight into the relationship between pressure and temperature. Now, ultimately, there's a direct relationship between pressure and temperature. So as the pressure goes up, well, the temperature of something is also going to go up. Okay, now all of those rules, including this one, this Avogadro's law, which Avogadro, we talked about him a little bit. We didn't really focus on him too much, but he's the namesake for the definition of 1 mole, 6.02 times 10 to the 23rd. That is Avogadro's number. So you have to imagine that Avogadro's law relates to an amount. And Avogadro's law presents the relationship between amount and volume. Now, at constant pressure and constant temperature, there is a direct relationship between the amount of a substance and the volume that that substance occupies. So if you increase the number of moles, if you maintain constant pressure and constant temperature, the volume is going to grow. So you're going to, if you add more moles of a substance, well, then that volume that that substance occupies is going to have to increase. All of this comes together in an equation known as the ideal gas law. The ideal gas law is PV equals nRT. Okay, so all of these different variables, P is pressure. It is listed in atmospheres. Okay, V is volume in liters. N is number of moles in units, MOL. R is the constant, and T is your temperature in Kelvin. Okay, so whenever I show you this, I want you to think about, well, what are some of the questions that I could see related to this? Well, one question that you could see related to this is going to present you with a number of different variables. So pressure listed in millimeters mercury, or pressure listed in torr, or something like that. So there's lots of conversions generally that you have to do with the ideal gas law. Now, one of the ways that I think that it's helpful to remember these units is to use this equation right here and rearrange it. Rearrange it so that PV is divided by NT, leaving behind R. Now, R is the ideal gas constant. The units for R are liters times atmospheres divided by moles times Kelvin. Okay, so now let's look back at our equation. PV divided by NT. Well, pressure is listed in atmospheres, right? Volume is listed in liters. N is listed in moles. And T is listed in Kelvin. Okay, so when we look back at the units right here, liters times atmospheres. Oh, we saw that. Atmospheres times liters. Divided by moles times Kelvin. Well, heck, if you know the units for the ideal gas constant, you can deduce or kind of reverse engineer the equation for the ideal gas law. Okay, now you can ultimately relate all of this to conditions known as standard temperature and pressure. STP is defined as, standard conditions where your temperature is 0 degrees Celsius and the pressure is 1 atmosphere. Okay, now when you take that 0 degrees Celsius and you convert it to Kelvin, it's 273.15. Okay, now if you plug all of this information in, and if you take this information, so your temperature data, T equals 273, P equals 1 atmosphere, and plug that into your equation, including your R value, what you can ultimately solve for is, if you go with N equals 1, you can solve for V. And that V is going to be 22.4 liters. So you can kind of use this as an additional definition. 1 mole of any gas at all, at STP, 1 mole of any gas at STP occupies 22.4 liters. All right, well, I hope this was helpful. We'll continue on. We've got 2 more videos, 2 more lectures related to gases, and that'll be it. All right, well, I hope this is helpful. Talk to you later.